One of the topics that people have been talking about is AI and blockchain, right? And I think there have been, a fair amount of conversations around that. But we have an expert today with us who's going to dive deep and give us some insights in terms of what does AI need from blockchain. So, friends, I'm very happy to welcome Ed Felten. Please give a round of applause. Ed is the co-founder and chief scientist at Offchain Labs, who are building Arbitrum. And we were very fortunate to have Ed with us as a keynote speaker at DevCon, at the Rollup Day in DevCon in Bangkok. So thank you so much, Ed, for giving us your time today.
Thanks. Okay. So people are talking all the time these days about AI and blockchain. People want to put AI models on chain. They want to use AI to help them manage their user interface, to help them manage portfolios, and in general, they want to use AI so that their activity on chain can be even more 24/7, even more active than it already is. So, as a person who works all the time on designing and improving rollup protocols, I wanted to just ask, what is it that AI needs from us in these protocols, and how can we provide it? So the big division here, if we break it down, is between Offchain AI and Onchain AI. Offchain means that there is an AI agent that's operating on behalf of a user or an enterprise, but that entity is not on-chain. It is a client or user of the chain. An Onchain AI, of course, means that you're taking an AI machine learning model and you're actually executing it on-chain so that you can have the transparency and provability of being on-chain. So first, let me ask, what does off-chain AI need? Well, I talk a lot these days about how it is that we can be aligned, or, in the Ethereum world, people are always talking about Ethereum alignment and accusing each other of not being aligned and so on. But to me, what alignment means is just this, that we're working all the time to make the Ethereum stack faster, cheaper, more reliable, and easier to use for users and developers. And so when we're doing this, what does this, how do we bring AI into this? Well, the starting point is just to recognize that now some of our users are AI agents. Maybe some of our developers are too. That probably has less impact than what we're building. But in terms of what AI is doing and wants, the fact that many of the transactions that happen on chain are coming from AI agents, or will be coming from AI agents, rather than from humans clicking things, or from other kinds of bots, may be significant. Because AI agents, I think, want these things even more than people do. Certainly when it comes to speed, AI agents, something that's fast for a human, like 100 milliseconds, is probably not necessarily fast for an AI agent. And if AI agents are more active, they're more actively, say, managing someone's portfolio, they're doing more transactions, they care more about cost. So we really need to just keep doing the things we're doing as a starting point. Of course, when we talk about trading agents plus low friction trading, low cost, high speed, etc., the result is a predicted DeFi Cambrian explosion of functionalities as people come up with new products that are not just tokens that sit there and maybe accrue value, maybe don't, but instead more actively managed portfolios that people have participation in. Okay, so there's a lot of things we can do to try to make it fast, and I'm not going to go through this in a lot of detail, but we need to understand benchmarks to make things faster. How can we execute faster, execute in parallel? How can we price the resources of chains more accurately so that we can get more useful work done within the same with the same hardware? And finally, how can we shard by having more chains while having those chains work together? Horizontal scaling is a really important part of this. Horizontal scaling just meaning that instead of having one execution engine, one chain, you have many chains. And of course, here's the obligatory photo of Arbitrum chains that are currently live, at least a subset. There are currently about 130 chains in the Arbitrum ecosystem. And of course, more every day, chains in other stacks as well. If you are providing Rollup as a service, then you probably have a lot of customers and ever more. This is a great example of how we can add capacity And in addition to there being more of these chains, many of them are specialized. They're customized for particular use cases, and that also is a really important part of this proliferation of chains. The fact that a chain can be specialized, different governance, different economics, different tuning for different use cases. Okay, how do we make it cheaper? Well, there's a bunch of things we can do, but ultimately, we want to lower the cost of operating a chain, because at the end of the day, the cost of operating the chain is going to flow through to users in the fees that they pay. We can maybe in the short term subsidize fees, but if we don't have a low cost of operation, then we're losing. And we focus all the time on trying to drive down the cost of operation of a chain without making the chain's behavior or performance worse. And one of the things we can do there is better pricing. In particular, resource pricing these days is typically done through some one-dimensional gas, and there's a gas limit, and if more is happening on the chain than the gas limit, we raise the price. We can be smarter than this, think more carefully about what are the truly scarce resources on the nodes and validators of a chain, and how can we make sure that we don't limit or increase price unless one of those scarce resources is actually under strain. By doing this, we can get more done at the same, with the same hardware. And finally, one of the really important pieces here is to connect everything. We have hundreds of chains. Users have assets on one chain. They have activities they want on another chain. Liquidity is fragmented. What can we do to actually connect these things together in an effective way? I think that when we think about how to interoperate among multiple chains, we need to think about taking an example from the internet. The internet is probably the best example of effective interoperation that exists anywhere in the technical world. And there's this recipe that the internet has followed, this approach to interop that's been so successful that I think we can emulate as well as we're building out an interoperable multi-chain world. And that means focusing on interop that's fast, that's standards-based, that's asynchronous, meaning you don't stop and wait for the other party, because who knows how long it's going to take them. That's fault-tolerant, meaning that when interacting with some other party, some other chain, you don't assume it's necessarily going to be there or necessarily going to respond quickly. And it's also security conscious, meaning that if you're interacting with something or someone, you don't assume that they'll necessarily behave correctly, but you take care of protecting yourself. You allow users to make decisions about risk and trust, but you don't hardwire those into the system if you can avoid it. We at the Offchain Labs team have been working with the Arbitrum community on what we call the Universal Intent Engine. This is a framework for providing cross-chain interoperation that allows users who have an intent to do some cross-chain operation to be matched up with solvers who are able to provide that operation. So if I have funds over here and I want to do a trade over there, I advertise my intent, and solvers can compete to get my business to execute that operation over on the other chain, critically in a way that is trustless and very fast. Okay, so, and of course that is especially important. Universal intents and cross-chain activities are especially important in a world with AI, because if there's one thing that AI agents can be good at, it's spotting opportunities across the whole ecosystem. So if my AI agent is scanning 250 chains and it sees, hey, I see a price mismatch between a market over here and a market over there, I'm going to jump on that. That's going to require a cross-chain operation. And so I think that as we build out this AI-centered ecosystem, we're going to see more and more need for cross-chain operations, and for those to be very fast, trustless, and extremely reliable. All right. Let me turn the page and spend the rest of my time talking about what does Onchain AI need. Offchain AI is the right thing when the AI agent is acting on behalf of a user, and that user can either run the AI agent themselves or find some entity who they trust to operate the AI agent for them. But if you're going to have something like a market that is mediated or managed or run by an AI agent, or if you need to have an AI agent that is neutral and counted on by multiple parties, then you're going to want to have that on-chain for the same reason that we put smart contracts on-chain, because of the transparency and accountability that it provides. But putting AI on chain is not so simple. The main reason it's challenging is that state-of-the-art AI machine learning models are very large. They have a lot of data, they do a lot of computation, and data and compute are relatively scarce on any blockchain platform. So how can we attack that? The big problem, the thing that is most challenging for putting large-scale AI on chain is proving. If you're in a rollup, you're in an L2, or even an L1, you need to have some way of proving to the participants in your protocol what is the correct result of evaluating some AI model on some particular input. So how are you going to do that in a way that's reasonably affordable, that doesn't break your assumptions about, say, cost or what types of equipment are being used by users? All right, so I got a little table here that talks about different approaches to trying to prove the execution of an AI model. And there's basically three approaches. The first approach is staking plus voting. This is sort of a traditional consensus type model. This is something like what Ethereum does, what some other systems do. So parties stake, and one party is chosen to propose what is the claimed result of the, in this case, model execution, and then the other parties vote thumbs up or thumbs down. If there are enough votes in favor of the proposal, it's accepted and treated as true. Enough votes against, it will be rejected, and the proposer will be slashed. They'll lose all or part of their stake. Right? So the second one is staking plus optimistic proving. This is what chains like Arbitrum and the OP stack use. This is a situation where parties make claims about the result of execution. And then if someone disagrees, there is a dispute resolution protocol that determines who's correct on the merits. And then whichever of the competing claims is decided by the protocol to be correct on the merits will be accepted. And then the third approach here is ZK proving. That is, somebody just produces one of these complicated mathematical proofs that the result of what the result is. And in terms of evaluating these, one easy way to do it is to say, well, what if somebody attacks this? What if somebody tries to get a false claim accepted? And there are two questions we can ask. One is, if they try, will they succeed? And the second is, if they try, will they be slashed? Will they lose funds? Right? With the staking plus voting, the consensus approach, because it's voting, you lose and you will be slashed, not because you're wrong, but because you don't get the votes. And so in a consensus system, an attack might succeed if the attacker can get it by or get or corrupt or confuse enough voters. And if the attack's detected, then the party will be slashed, but if it's not, then they won't. So in this kind of scheme, an attack might succeed, and if it succeeds, then the attacker will get away scot-free. That's not so great. In order to make this really secure, you need to have a very, very large consensus set, very, very large set of voters like Ethereum does. If you try to do this on the cheap, then you have a lot of risk. All right, second approach is staking plus optimistic proving, and this has the advantage that if there is a dispute, that the protocol will decide on the merits who's correct. And that means if somebody tries to cheat, someone else calls them out on it, the protocol will determine that the cheater is cheating. The attack will fail and they will always be slashed. All it requires is some party to show up and raise that challenge, which of course everyone has incentive to do because they get to take the stake. With ZK proving, the attack doesn't succeed, and in fact you don't have slashing either. But of course the drawback there is proving can be quite expensive. Okay. So let's talk about what happens if we just evaluate the model on chain. One of the things we might try to do is say, well, let's just take the model evaluation, we'll write it in Solidity, we'll write it in Rust and run it on Arbitrum Stylus or something. We'll just do the evaluation on chain as a regular smart contract. It's easy to do, it just works. But the problem is it's expensive and almost certainly violates your gas limit if the model is at all large. So this approach is kind of not going to fly. You're going to have some proving method which is specialized for proving the evaluation of machine learning models. Now these models, the computations to evaluate a model, are very structured, very special, unusual computations. And you can take advantage of that to try to build a specialized prover. Right? One thing you can do is say, well, let's try to evaluate the model in a coprocessor, a sort of side chain that's specialized for just this purpose. The advantage of this is you can use customized proving gadgets, which can make things a lot faster potentially, but the drawback is complexity and integration requirements. In practice, you probably have to do this because otherwise the cost is just going to be too high. All right, let's talk about how you might optimistically prove the evaluation of a model. And just as a reminder or a 20-second tutorial, these machine learning models are constructed out of units, sometimes called neurons, and each one takes a bunch of inputs from earlier in the network, multiplies each one by a weight, adds them up, and then takes that weighted sum and runs it through a simple process called an activation function. You just have a very large number of those that are all connected together. Okay, so how can we do optimistic proving? We start with the parties who might disagree about the result, each committing cryptographically to the outputs of all of the units in the network. Then you bisect over the units to find the first unit where they disagree. So we say, give us a hash of the first half of the units in the units in the first half of the network and the second half separately. We ask the other party to do the same. Now we can narrow down the dispute to the first half or the second half. Just keep doing this, narrow down the dispute until you find the first unit, the first one of these little neurons that the parties disagree about. Having done that, you now, if they disagree about what happens when you take the inputs of that unit and multiply by the weights, you could do a further bisection and find just one little multiply and add in that process where they disagree. Otherwise, they just disagree about evaluating this simple activation function. By breaking down the dispute into smaller and smaller pieces, you eventually break it down into a tiny piece that's very easy for an on-chain referee to execute. This is like what optimistic rollups do today, except just specialized to AI models. And the final thing you could try to do is ZK proving of model execution. And this is very feasible. ZK proving of anything is feasible in principle, but it's extremely expensive today. The main challenge is just the proving cost. You could try to design specialized proving gadgets to speed up this proving, make some progress there, but this is not really there so far. For models of realistic size with realistic data inputs, this is still just too expensive today. So we have more work to do. I'm far from having an answer for you for how we could do these rollups on chain or these AI models on chain, but it's an active area of research and I think we'll get there over time. I need to close my talk as always with the Arbitrum mantra, which is your chain, your rules. Thanks for your time and thanks to our friends at Zeeve for the invitation.
Thanks, Ed. As always, very enlightening, and I think we've all been enriched by this conversation today.